Hello everyone to this second video of our microservices series on Azure. My name is Nicolas and today I'm again with Stanislas. Hello Stanislas.
Hello, Nicolas.
So before we begin, let's have a look first at a definition of microservices. And to do that, we'll use the definition from Marcus Inovich himself. He's written a nice blog post that you can see on the link below. And his definition is that microservices are simply a way to break down a monolith application into smaller pieces. The goal is to have different developers and team working together on smaller independent components. And I think that's the very important aspect, the independence of each component, to work into a larger application. So essentially breaking down a large application into smaller and more simple pieces.
Okay, so we are dividing a monolith application into microservices. If we are looking here, very famous examples of companies that did this job a few years ago, because this picture are from 2015. It's very old now, but the idea is still there. We can see that if you take a monolith, divide in many microservices, it can you can lead to a very complex infrastructure where a lot of connection are done between all the microservices, and you can get at the end what we called an architecture that is a Death Star because there is too many dependencies between the microservices. So you have to remember that it's complex to transform a monolith application into microservices, and that microservices are not a silver bullet. It's not an answer to everyone, to everything, and sometimes it can, the result of dividing the monolith into microservices can be worse than having a monolith. So it's not a solution for every problems. But in many cases, it can be very interesting, and Nicolas will introduce just in the next slide what are the options and why the microservices are interesting.
So let's have a look at 4 benefits. There are many more benefits, of course, about splitting an application into microservices, but we just want to highlight 4 benefits here. The first one is really about independence for scaling. And we've taken the example of a very simple photo sharing application, and we're just going to demonstrate that with 2 services. One is photo sharing, and the other one is thumbnail. So the thumbnail will be triggered when someone uploads a new picture, and we're going to generate renditions and scale down the image. So if you have a lot of people consuming photos, then you want to scale the photo sharing services. And if you have a lot of uploads, you will want to scale the thumbnail service. And we can absolutely do that with microservices. We can scale independent services without scaling the entire application. So it's really here the concept of right sizing, not the infrastructure, not just for the entire application, but for a specific service and a specific need. And it's all about balancing cost versus speed. And that's especially interesting when we talk about cloud computing, where you are paying the resources on demand by the minute or even by the second, depending on which service you are using. So really about scaling up and scaling down the services whenever you need to. The second aspect to it is about choosing the right technologies. And by splitting the application into smaller pieces, you have more independency to choose the technology stack that you want to use. And we can, for instance, take, again, using these 2 services, we could write one service using .js and write the thumbnail service using .NET, for instance. That's just an example. If you talk about a recommendation, you might want to use a different technology for recommendation engine. And it's not just about the programming language, it's as well about the backend and the dependencies. So for instance, a database, you might use one database for one SQL database for transactions, and you might use a document-oriented database for the use cases, or even blob storage if you need to. So really, it's about choosing the right technology for the right feature you're trying to implement. Benefit number 3, it's all about versioning and how do you move from one version to the other. If you have a monolithic application, essentially you're bound to your colleagues and other teams to be ready at the same time as you are when you want to release a new version of the application. If you have bugs, if you have features that have not yet been implemented, you can either decide to go with a scaled down version or to delay the release of your application. And it can cause some frustration between the teams. That's what's interesting with microservices. You have more autonomy to deploy and release your application. So here again, the Sentinel service is moving from version 1 to version 2, while photo sharing and video sharing are staying at version 1. And then, of course, you see that there's a link between these services and the thumbnail services. So as an owner for the thumbnail service application, you have to ensure that your services and your API have backward compatibility in order not to break the entire application. And we have multiple options to do it. It can be supporting multiple versions of an API, so essentially having multiple versions into your infrastructure at the same time, or it can be baking the backward compatibility within the application, and that could be harder to maintain. So usually when we start to deal with microservices, a good way is to have multiple versions of your APIs. Point number 4, it's all about dependency management, and it's kind of related to the point number 2 about multiple technologies. Here the goal is to, again, give you the capability as a team to choose which dependencies you need. I've taken this photo sharing application again. If we had a monolith application, then we would be dependent on other teams to select which library to use, for instance. If we split that down into microservices, each team can upgrade dependencies at their own pace. And the photo sharing service can stay in version 1 of the dependency library, while the thumbnail service can move to a new version if they want to use new features or if they want to take benefits of a bug fix in a specific library, for instance. So that's, again, very interesting when it comes to doing upgrades, doing technology choices. You're not bound to having a long meeting and doing trade-off between which version to use. Here you have the ability to take your own technology and to evolve the piece of software at your own pace without, of course, breaking the entire application. So I've talked about 4 benefits of microservices, but there's much more to it. So let's have a quick look at microservice in a nutshell and what are the other benefits we can get out of it.
So first one is you are trying to make one process per microservices. If you can do that, it's better because it's independent from the other process that are in other microservices. First point.
Second point, each microservice has its own data store. So you're able to select, again, the type of data store you want, but you're able as well to pick your own schema. And you might end up with duplicated data, but that's okay. You have more isolation to handle your workload and the way you want to process the data for each microservice.
You will have also an independent lifecycle for each microservices. It's very important because, especially if you are working in a DevOps organization, as we talked already in the previous video of this series, if each microservice is built and run by an independent teams, it can have its independent lifecycle. So you don't have to wait another teams or another microservice to do the next version. If it's ready at one time, you can deploy it and the new version. If it's not an issue. You just continue to improve your code, and then you deploy when you feel that you are ready to run these new services.
Right. Other benefits, minimal dependency between microservices. We mentioned the DEFTA architecture. This is what we're going to try to avoid. Again, microservices are not a silver bullet. And if we're not careful with the dependencies between microservices, we can end up, just like we have spaghetti code in a monolithic application, we can end up with essentially spaghetti microservices and too much dependency. So we'll try to have minimal dependency between each microservices, and we'll try to enforce loose coupling between microservices if there's any dependencies.
Yeah, we'll have also an independent scalability. A microservice can be very used, another can be used more often. So depending on the demand and the usage of your microservices, you will have to scale it independently. And it's very, very interesting, especially when we will talk about later about containers and about, for example, serverless and code that is deployed just for the need. You have to do that.
Other topic, we mentioned that so microservices tend to be smaller, and it's better if they have like smaller pieces of software, which is This is why we call it microservices. So essentially, we will have smaller and more frequent deployments. The release cycle will be faster as well, right? If we need to implement new features, if we need to fix something, we can have a shorter time to market with microservices if it's done correctly.
Yeah, so as we already say, we should be loosely coupled. Microservice should not depend directly on other services. So you will use some systems like queue or bus, for example, for not having a direct connection and couple two microservices together. You will have a distributed system, and it will be elastic if you scale it independently.
And last point, and that's back to point number one, actually. So we have one process per microservice. We want to have resource isolation. It can be at the compute level, or it can be through other mechanisms such as container that we'll address into the next video. So essentially making sure that we don't have this concept of noisy neighbor when one service or one feature of the application takes up all of the resources and impacts the rest of the application. So here we can have isolation at the service level as opposed to at the application level. And we can have dedicated CPU, RAM, storage, IOPS, even networking for every single microservice. So these are essentially some of the benefits of microservices. And of course, it's a new way of developing applications. And when we talk about application development, we have some key patterns as well that we need to understand, that we need to master before we can be proficient in microservices. The first one is decomposition by domain. We talked about splitting an application into multiple sub-applications. So how can you do it? You can have a look at the functional features, or you can have a look as well at the domain. And the domain essentially is having at how your business is organized and splitting the application based on by multiple domains, and having a direct link between what you're implementing and the feature and the business organization that you're trying to that you're talking to into your company. Second aspect, it's all about database by service. So we mentioned that we don't want to have a single repository for all the microservices. That would simply create too many dependencies. That would create some schema dependencies, and essentially you'd be ending with something where you lose all the agility that you want out of microservices. So one database per service, and potentially some data duplication. That's okay. There's some patterns that we'll talk about to address that.
To be more precise, it should be one data store per services. It can
Right.
be a database. It can be also a simple storage like a blob storage, or it can be a cache in memory like a Redis cache, for example.
And when we talk about database, it doesn't mean a dedicated server. It just means a separate table, for instance, but not necessarily the entire server. And that's a discussion we had with a few customers. Doesn't mean that you have to provision a new license and a new server. You can have essentially a separate schema for your service, but you need to find the right trade-off between the cost, the performances, and the agility that you want to get. Point number three, it's all about APIs. Microservices tend to be APIs oriented. This is how we're going to create a contract between each microservice. And in order to organize this communication, we want to have a very consistent way to consume API, to consume and expose API. This is why a good pattern is to have an API gateway. And when we talk about the front end, just like we want to split the backend into multiple microservices, we want to have some agility in the front end. It wouldn't make sense to have a monolithic front end calling a microservices application, because then we will end up with, again, a long backlog and some reduced time to longer time to market. So to do that, we can introduce some patterns such as the backend for front end, aka the BFF, which is essentially having a piece of API and having the front end again split into multiple layers that will be that will call services through APIs. Point number 5 or 4, I think. Yes, point number 4. It's all about circuit breaker. So that's again one pattern. We will call potentially other APIs. We will have some dependencies to other APIs or other services. We don't want to break our service if another service is not behaving as usual, and we don't want to create a chain reaction where one service essentially breaks down the entire application. We need to have resiliency baked into each microservice, and we can introduce patterns such as circuit breaker. So the concept is that if one of the dependencies is not working, we will delay the call to that service, and after 1, 2, 5 attempts, if it's the service is still not working, then we will just shut it down and not call that piece of code. So for instance, if it's a database and the database is not responding, we have other options. Yeah, we can store the transaction into caching. We can put that into a bus or a different storage in the meantime.
Yeah, that's the beauty of a microservice architecture. If there is a problem with one part of the global solution, one microservices, it doesn't not impact all the whole application. So that's really a change of paradigm between the monolith, where something can break all the monolith. Here, if something is break, one microservice can be broken, and it's a rule of the teams to run it, so to change what is not working, but it will normally not impact the whole application. You can imagine, for example, a website, an e-commerce website, and if, for example, the search engine or the recommendation is not working for some hours, it will not break all the system. People can still add things to the basket and pay late and pay and get their product.
Exactly. So again, let's have a look at, and that's back to the point of how you split your microservice application. That's why it's important to have a good split by domain in order to isolate features and still have an application that can fulfill some of the features and business scenarios if one piece of application goes down. And the e-commerce example is a very good one. If your recommendation engine is broken, it's annoying for upsell, but it won't break the basket and the fulfillment process. So we have multiple microservices for the backend, and again, we can do similar type of behaviors on the UI. So using UI composition pattern and essentially building at the runtime the UI based on the services that are being called and on what the user preferences are. So we can essentially not have a static application, but have some piece and components that are loaded at runtime. And again, like single page applications are a perfect way to do UI composition. Another point is all about service registry. How do you know that a new service is available, and how do you essentially communicate what's the endpoint and what's the contract for a new service? We can use a concept of service registry, where we can query what's the location of a given service. So you mentioned recommendation. Recommendation service can have maybe multiple versions of the API. It can have multiple locations as well, if you talk about a distributed architecture. And we can use a service registry to find out exactly what the available endpoints for a specific service. And last but not least, it's a bit more complex, so we'll spend some time on that. We'll talk about the Saga pattern.
So do you have any recommendation about some readings, books about microservices and patterns?
Good book, and actually it's a bit hidden by you, Stan. Right below we have microservices.io, and behind this website is as well a book which is available, and it's a very good read that I recommend. It's Microservices Patterns, and that's essentially extend what we just talked about. So a lot of other patterns are available when we build microservices applications, and you can start to discover them online. And you can as well get that book that I personally started to read last year, and I think it's a great way to start to better understand how to build and architect microservices applications.
Yeah, you just said that you will talk about the Saga pattern. That is an interesting pattern because during our meetings together, with some partners and customers, we had a lot of people that were asking some question about the fact that we have one data store per microservices, and that it can be complex to manage all the transaction. Maybe you can talk more about the Saga patterns now.
Yeah, so the Saga pattern is about how do I handle a transaction which spans not one, but multiple microservices. And then if it spans multiple microservices, then it will span multiple data store, because back to our point, we have one data store per microservice. So what happens, the question is, what happens if one of the service breaks down, right? And the name of the Saga pattern comes from essentially a story spread on multiple books. So maybe Lord of the Rings is actually a saga, and this is where the name of the pattern comes from. So this is the same. We're going to take a transaction and span that transaction not in one single service, but into multiple services. And the goal of the Saga pattern is to have best practices to manage errors for each component, and we're going to use what we call a rollback system, so a compensation mechanism, where we are able to roll out individual transaction for each microservice if the entire scope is broken. So let's have a look at an example. I think it's going to be a bit more efficient. This is very fictional because we're 2020 and travel is not an option. So probably this transaction is actually not the best, but ideally we're ready for next year, and we're going to book a travel again. So when it comes to booking a travel, usually most of the time you don't just book a plane ticket. You want to book first the plane ticket, you want to have a hotel reservation, and probably you want to have a car rental or a taxi, right? So we have here 3 items. It can be more, it can be less, depending on the way you travel. But if you book something, what happens if then the hotel reservations failed? What happens if all the hotels are booked in your location? Or what happens if you book the hotel, but then the airline is fully booked as well and it overflows your budget? You want to cancel the entire trip. Or if something else happened, then you want to cancel everything. We need to call multiple sub-services to cancel everything. So here we have an example where we've booked everything, and then unfortunately the airline just canceled our flights. And this is actually quite common. Maybe there was booking was they overbooked the flight, or maybe there was an issue. Once we booked the hotel, then the flight was fully booked. Then everything can happen. So how do you cancel that? How do you maintain consistency for all the services? Well, this is exactly what the Saga pattern takes care of. And here, essentially, the booking of the hotel now failed, while the booking of the flight is okay. So first, the hotel failed, so we don't want to book the transportation. It doesn't make sense. We're not going there at this stage anymore. So first, we want to revert the hotel booking. It didn't work. Because we reverted the hotel booking, we want to cancel the booking of the flight. So the flight booking will be in a pending state, which means that it will only be validated once all the other transactions are validated, but we want to make sure that no one else picks our seat in the plane. So we're going to save that, mark that as pending, and once all the other transactions are completed, we're going to validate each transaction. So that's a way to distribute one process, which is a booking process, into multiple services and multiple transactions, while still keep being able to roll back the entire transaction if something happened. And then, of course, if we canceled everything, then we want to cancel the plan as well. So we want to roll back everything. And then we are back to a known state. We haven't spent any money. We haven't booked a flight that we're not going to use, booked a hotel, and so forth. So it's really about orchestrating multiple services and being able to manage issues into a multi-service process.
And into a multi-service with multi-data stores also.
Exactly. So you want to keep consistency at the transaction level, but you want to keep consistency as well for every single data store.
So when we saw that, we understand more clear. It's more clear that when you said before, microservice is not a silver bullet. That means microservice will help you to define a new way to construct your application. but there is still a problem because it will add some more complexity, and you will have additional choice to do because you are changing in a monolith application. It's very simple. You have one monolith, one database, and you
Right.
can
You have one database,
yeah,
and
you can
essentially you have a travel, then you have a flight ID,
yeah
hotel, transportation. If something happens, you
at the
cancel
end.
easily into a
Yeah,
single
okay.
transaction, right?
So it's more complex when you have more data stores, and that's why these patterns are important to know and to study. And you have a link here on Microsoft website where some patterns are very well explained.
So we've talked about a few patterns, and we talked about the Saga pattern. Essentially, the idea is to have better resiliency on the overall application. So let's have a look now at how we're supposed to transition the way we manage applications and processes from a monolithic application to microservices.
So first thing is you have to change your way of dealing with your services and transit from the pet to the cattle way of life. So I explain. When you have a pet, for example, this small kitten, you get it. It's very small, very young. You give it a name. And you try to keep it as long as you can because you love it, you take care of it, and it will grow. It will become bigger if you give him some good food and if he's healthy. It will change because it will become older and older. And sometimes he can be sick, so you will go to a specialist that will try to manage the problem. And later, as late as he can, he will die. So
That's
yes,
very sad. It's very sad stuff.
yeah, it will be the only sad part of this webcast. Trust us. But in information systems, we have a lot of pets. If you have a server, you get it. It's very young. It's a new brand server. You install an operating system on it. You give it a name, SQL DB01, for example, and it will change during the time. It will grow. You will add some data. You will add some more disk. You will change the configuration. Sometimes you will have some issue, and you will call a specialist to help you to deal with. And after long years, probably this server will die because it will be not used anymore, and so you will have to decommission this server, and it will be its end of life. On the other side, it's a traditional way to manage a computer in a monolith approach or in the standard way we use for many years. On the other side, we have the cattle approach. In the cattle approach, here you can imagine that you have cattle. You don't really give them a name, it's just a number or an ID. And if you are the farmer that has all these cattle, you don't really care about each individual. You care about the whole group of cow, and you are dealing with the demand of your buyers for this cow, for the food, and so on. So there is no affection, and you are just trying to manage the right size, the right number of cows depending on the demand. So in computer, when we are dealing with cattle, it will be the same thing. For example, if you have a web server, a web form, it's a group of servers. But factually, you don't care about each individual. You care about the group, the firm. And in this web form, what you want is that the form is available with the service that are providing. So if you are losing a member of the form, it's not a big deal because the form is still there. And you just have to adjust the size of the forms depending on the requests that are demanding the service on this form. And that's why the name of each server, you don't really care. It can be X, I, Y, 1, 2, 3. You just want a group of servers that are just giving a service, and that's all.
The services, we have something where we can scale up and scale down based on the demand. And because we're doing that, we need to change as well the way we configure servers and applications. So on one end, on the old way of doing things for monolith applications, we are more tending to use the mutable approach. And mutable, just like Mickey Rourke, is something that evolves in time and that changes. So going back to the concept of servers, a mutable server is a server where you will update. So you will essentially bring new version of the operating system. So installing patches, you will then connect to the server and install new version of the application. So it can be through a CI/CD pipeline, but essentially you're keeping the same instance of your server and patching that instance to bring a new version of your application. On the other hand, we have the immutable concept. Here we took the example of Tom Cruise because, unfortunately, the new Top Gun has been delayed to 2021. But if you have a look at Tom Cruise in Mission Impossible 1 and Mission Impossible, I think we are number 6 now, it still kind of looks the same, right? So essentially, it's not something that changes. Immutable does not change. It's being replaced. And back to the concept of servers, if you have a service that needs to be updated, maybe you need to update the operating system, maybe you need to update to a new version of your application, we're not going to do in-place editing of our server. We're going to bootstrap a new server. So back to the concept of cattle, we're going to create a new instance, and we're going to destroy the old one. We're never doing in-place editing. We're not doing patching of individual servers. This is something that does not scale. We have the concept of immutable. If something changes, we create a new one and we destroy the old one. That's the key concept of immutable. So it's best to have immutable. And for that, we need automation. And we'll talk about it a bit later.
And also we'll talk about two approaches of frying versus baking. If you want, for example, to create, if you're hungry, option one is.
Oh, you mean if you're hungry? If you're hungry, I'm not angry. I'm just hungry. It's almost dinner in Singapore.
Okay, so if you're hungry, you have to prepare your food. So approach number one is, for example, here with the meat, you take your meat, you put some stuff here, you put the meat in the fridge, and when it's ready, it spend time with spices and many other good things. When you want to eat, you take the meat out of the fridge, sorry, and you go to the barbecue, and you have to fry the meat on the barbecue. So between so the preparation can be very short time, but when you want to eat, you still have something to do, and it can take time. So I explain now with a web server. So you have a web server, you want to deploy a new version, so you want to prepare your server. So to prepare your server, what you can do, you can prepare a master. So for the master, you prepare, for example, the operating system, you update the operating system, and you set up, for example, the web server, an Apache server or an Nginx or thing like that. And you package your image. It's your gold image. And when you want to create a new server inside your web form, you will create a new virtual machine using the golden image. And during this process, at the end of the creation of the VM, you will launch a script to install the latest version of your application. So finally, to get a new server inside the form, it will take the time to create a new VM and the time to run the scripts that will download the last version of your application. So it's what we call the frying approach. On the baking approach, it's little different. You take all the component of your food, you bake everything, you put it in a box, and when you are hungry, you just open the box and you eat. So there is the time to market for eating is very, very short, but the time to prepare is longer. So now we will come back to the web server. If you want the baking approach for the web server, you will prepare everything. That means you will prepare your golden image with the operating system that is up to date. You will install inside the web server, the Apache, the Nginx, and also you will put inside this golden image the latest version of your application. That means when you want a new server in your form, you just have to create a VM based on this image. So as you can imagine, it takes longer time to prepare an image with everything from the operating system to the application and its configuration. But at the end, the time to market to deliver a new server with a web application is really shorter. So you spend more time before and less time when you need really a web server. So that's why we will probably use for the baking some pipelines to automate everything, because every time you will change your application or your microservice, you will have to rebuild a new image to use this as a baking. So that's a baking approach.
And I think the baking, as you mentioned, takes more time to prepare. It's way faster when you deploy your application. And if you go back to the 12-factor app, we mentioned the time it takes to bootstrap your service on application. So that's quite important. The drawback is, it takes more time to prepare. And it will take more space as well in your registry, whether it is an image gallery or another type of backend that you will use to store your versions.
Yeah, but of course, because microservices are involving very often, the goal is really at the end to have an automatic system that will baking for you, will do all the job for you. So we'll talk about this later.
Right. Other topic, it's all about imperative versus declarative. You mentioned the frying and baking. So when you create, like when you do baking, so essentially you want to prepare everything up front. And there's two ways of doing things. The first one is the imperative way. So I took this very example of an IKEA bookshelf. And this bookshelf essentially comes into pieces and you have to assemble that. So what does it mean when we talk about IT? Let's say, getting back to the example of the web server, if you want to install a web server, if you take Apache, you'll have to download the dependencies. You have probably to install a few bits of software on your operating system. And then you will configure the Apache and start the service, and it will listen on port 80 and on port 443 if you're doing a good job and doing HTTPS and TLS. And what happens then, of course, you can automate that through a script, and that's fine, right? You can do a PowerShell, you can do a CLI, and the script will run perfectly the first time. Of course, you'll have to test that on your dev environment, and it will work the first time. But then what happens if you run it the second time? It will fail. That's what's going to happen. And it will fail simply because port 80 is already listening. Your web server is already up and running with a specific version. So that means that if you want to run that script again, you will have to roll back all the changes. And it can be simple for just a web server, but when we talk about application dependencies, web servers, file system, and other piece of dependency that you need, it can become super complex. And thinking of every single item in a script that you need to roll back or check is just too complex. So imperative essentially is running a script, doing step by step, and this is a concept of, there's no concept of idempotency. If you run it a second time, it's probably not going to have the same behavior. On the other hand, if we take that bookshelf again, the other way is to just order something pre-made, and somebody will just come up with that bookshelf ready to be in your living room. So here we have another approach. We design the specs. We say we ask what's the final state of our living room. So here we want to have that specific bookshelf. The mean to achieve that is none of our concern. We define the desired state. And that's exactly what we do into a declarative state. We don't write the script, and we don't do a diff between what's on my current environment and what's the new state of my environment. What we describe is what's the state of the final configuration. And we use configuration files, so most of the time it's YAML files, and we describe what we want at the end. So back to the web server, I would simply describe that I want an Apache server with a specific configuration, listening on port 80 and 443 with a specific certificate. Now, the system, a tool, will compare my current state and my target state. And if there's nothing to do, nothing will happen, right? No action will be taken. If the server is not installed, then the tool will detect that Apache is not here, that the certificate is not here, and will essentially create all the steps to achieve that need. So we have this concept of idempotent. We define the target state, and every time we run the tool, the target state is achieved. And this is much more powerful than having to write imperative code. So we always favor declarative to imperative, and that's back to when we do baking. We try to do baking through declarative files.
Yeah, and finally, if we combine all the four things we talk about, so if you combine mutable plus pet plus fraying plus imperative, you will get something. And if you combine declarative with unmutable, with baking, and with
Declarative.
with cattle, yeah, you will get this. So Snowflake is something that is unique, as you probably know. So every time you are using a mutable, imperative, fraying, and pets, you get a Snowflake versus the Phoenix. Nicolas, explain why the Phoenix?
Right. So the Phoenix is something that can rebirth as it is, right? So it can rebirth for forever. And if we take back the concept of an application or a server, if you have a Snowflake, then because it's so unique, if you try to recreate the exact same one, you won't be able to achieve that. That's too complex. We don't know how to do that. And that's unfortunate. That means that if your server goes down and you recreate that, you have something fairly similar, right? Snowflakes look similar, but they're not the same. And that will introduce some changes into your application, and potentially it will introduce some defects. If we take the other approach, we have something that we can recreate forever at an exact copy of your server. Then, if your server goes down and you recreate the exact same version, then your application will work as expected. And that's the concept of Phoenix. So being able to recreate something like recreate an exact copy of your server or of your infrastructure.
And when we talk about microservices, we are trying to think about the Greenfield, but in the real life, Greenfield is the exception and Brownfield is the norm. So by Greenfield, we mean an environment where there is everything to build. So you have a new project and you decide that you will do microservices because it's now the good, probably a good solution for the future to get a cloud-native application. But it can be dangerous to have the right to do what you want and start from zero and try to build everything, because you can have too much freedom and you can probably do some choice that will not be the best one. Most of the time, you will not have this opportunity to do everything you want and starting from zero. You will have to deal with some systems that are already in place, probably some monoliths, probably some database, probably some regulation and security rules and things like that, and probably also some competencies that are inside your companies. So we call that the brownfield. So it's not really a big deal to start doing some microservices in a brownfield. So in an environment, an information system that already have some pieces and you have to deal with, because it gives you some, it helps you for some choice, and you have to remember that most of the systems are brownfield, and now there is more and more projects that are starting to use microservices, despite the fact that there are some brownfield. For example, I have here in my hands my phone, and on my phone, one of the application of the multiple applications that I'm using, it's banking. I'm not going anymore in my bank agency because I can do
Actually, you
everything.
can't. So yeah, and you can't do it as well, right? So you're in lockdown.
Yeah, because it's locked down because of the COVID. But still, I was not going in my bank agency as the physical facility because I can do everything I want on my mobile. And this part, it's a differentiator between different bank companies. Because at the end, most of the users are now doing the same thing as me. They are using their phone as the main interface between the bank and their needs. So now, in most of the bank, you have some DevOps teams or product teams that are working just specifically on the mobile application. And as you can imagine, bank is probably the best place for Brownfield because you have some systems that were designed dozens of years before with some language that probably the youngest of us will never use, like COBOL or things like that. But it's still working. It's still working, and it will take dozens of years to change that. But in the same times, our customers are more demanding. They want to do some more feature. They want to send money very quickly. They want to pay with their phone. They want to use the facial recognition, the fingerprint also. So all these features need to involve very quickly with the technology. So you have to be in this approach, you can change your application very as quick as possible if you don't want your competitors to be better than you and your customers to switch from your bank to another bank. So if the bank can do that, and they have, I think, the biggest brownfield in the space of information system. Everybody can do that. And Nicolas, I think you have a story about a greenfield that was not a good and not very good
Right,
finally.
exactly. So, first point, Brownfield, you're right, it's the norm, and it doesn't mean that you cannot do microservices. Of course, you can do that. You can first evolve your application into small bits, implement new features as microservices, and slightly move toward a more advanced architecture. And you're right, Greenfield is the exception. It's like usually super interesting. People want to work on Greenfield. They don't want to have technical depth. But Greenfield is as well quite dangerous because if someone tells you that you have a blank check, it's very easy to get overexcited and take the wrong decisions. So I had a project where the team was like, well, we have to develop a new product and it's greenfield, it's great. So we're going to pick, microservices, obviously. We're going to choose containers. We're going to choose an orchestrator. On the database, we're going to take a NoSQL because, like SQL, it's so passe and it's not trendy anymore. We're going to use an event, but we're going to use Kafka for the communication, and to process the data, we're going to use something different. So a lot of trendy technologies, but then why did you pick this individual technology? They picked only clustered technology, which means that first it's kind of hard to maintain, right? If you don't know what you're doing and how to manage a cluster, you're in trouble, right? Your application might look trendy, but if you don't know what you're doing, you're not going to be resilient. Same happened for Kubernetes. It's super powerful, but if you don't know how to maintain a Kubernetes cluster, you're in trouble, both from a security standpoint and a management standpoint. So they got overexcited by picking new technologies for just picking them because they were trendy and not thinking the whole for the entire application. So they were essentially using new technologies and coding the application in kind of old-fashioned way. So essentially coding like not building microservices, but like essentially a distributed monolith. That's what they were building, an overly expensive and complex distributed monolith. So it's a true story, and we do see that from time to time. So Greenfield, you have to be careful. You have to make sure you master the technologies and you take the right decision. Otherwise, you're going to end up in a brownfield very, very quickly. And Brownfield, let's put that in motion. Let's see an example of an application built using microservices. This is an application called eShop on Containers. It's one of our reference architecture for microservices, and it's all available in GitHub. You have multiple flavors. We have Kubernetes, we have Swarm, if that's still a thing, and same, we have Service Fabric as well, if you like this type of microservices architecture. So it's a very simple e-commerce store to sell .NET goodies. So it's all about .NET. Some of the services are written in .NET, some of the services are written in other languages. What you can see here is we have, it looks like a very simple application, but behind the scenes, we have multiple services. The first one, on the top right corner, Stan, it's the login service. So we have authentication, we have the user database, and we have as well a mean to get role-based access control. Then right below that, we have a marketing campaign. That's a marketing service that is essentially going to do targeting and customization based on who you are. So if I'm logged in with a specific account, I will see something different. Right below that, we have the catalog. And the catalog is all about putting the products, putting the prices, and as well, then if you see in the catalog, we have the availability of that product. So essentially, is it in store? Is it sold out? That's some information we need to know. And actually, that's a different data, right? So the stock and the availability of a product compared to the catalog itself is different piece of information. And in the catalog, we have the pricing, we have the images, and we have the description of the product. And that's pretty much it. Right below a product, we have go back to the previous slide. Yes, we have the button to add something to our basket. And when we add something to our basket, it's a separate service. And the next step is to have the shipping and the fulfillment. So essentially paying for our order. So these are multiple features that we have into our application, and each feature is into a microservice. So let's have a look at the overall architecture. We have on the on the left-hand side, sorry, we have multiple clients. So we can have a mobile application, just like your bank stand. You can have that. You can go onto into the website, and we have two flavors for the website. The first one is a web app, like a usual web app coded in ASP.NET, and the second one is a single-page application developed in TypeScript and Angular. We have the front end as well. So we have a layer that is going to dispatch some resources, some HTML content, JavaScript, and some images as well, icons. And below that, then we have the implementation layer with the business logic. And we have 6 services, so 6 microservices, which can share some information as well through loose coupling using a service bus. So if you zoom a bit on the right-hand side, we have here, service communication. So that's a service bus that is essentially helping to do transaction and send information across multiple services without having a direct dependency for all of these services. So there's still some information being shared, but no direct dependency. All right, let's have a look at what it means from a technology standpoint. We have the eShop. The web app is an ASP.NET Core MVC application. We have on the right-hand side the 6 microservices, so identity, catalog, ordering basket, marketing, and location services. And you can see that for each service, we have one or multiple instances of each service, especially for the ordering microservices. We have an ordering API and we have a worker behind the scenes. And we see as well that we have multiple data store for each service. So we have a data store for the ordering, and this is very transactional. So we have a SQL server. On the other hand, the basket is something which is transient, which is not going to keep for more than 30 minutes or X number of, well, we can keep it for a bit of time, but it's something where we want to enforce a quick access, and for that we have a Redis cache. And marketing, we can have different type of data. We can have a MongoDB or Cosmos DB, so we're going to use NoSQL. This is really putting that to the extreme. You don't have to select so many different technologies, but that's to showcase that microservices are independent, can be scaled independently, and can select their own technology. And on the event bus part, we're using PubSub to send some events. It can be RabbitMQ. If we go for PaaS services, so platform as a service, we can use Azure Service Bus, for instance, or even Event Grid, or even Hub, right? So that type of services we can put in place. And then last bit, it's all about how do we deploy these. We talked about baking. We baked essentially these services using Docker. So every service, every microservice, each microservice, sorry, is a Docker image and is being deployed into an orchestrator. And we'll talk about containers specifically in the next video. So
yes.
That's the end of that specific video. So Stan, tell us what's next.
So what next? In the next video, we'll talk about containers. So we will make an introduction of what are containers and the basics of lockers. And we will explain why it's very interesting to use it, especially in the case of microservices, because we will follow all the rules that we explained before, the pet versus the cattle, the mutable versus the immutable, the frying versus the baking, and the imperative versus the declarative. So we will talk mostly about Phoenix versus Snowflakes, and we will make an emphasis on the Phoenix parts. So we'll introduce as much as possible for you to understand the basics of containers, and later we will talk about how to orchestrate all the containers together.
Cool. So much more technology oriented. Yeah. Snowflake, you mentioned that we're not talking about the database. We're really talking about the concept of Phoenix versus Snowflakes. And we'll go deep dive into containers running on Azure. And it's going to be a huge focus on the Azure cloud in the next topic.
Thanks for your attention and see you in video number 3. Bye.
See you next time.